So now we are going to discuss about the OC test on a transformer. OC test is also called as the open circuit test. So with the help of this open circuit test, we are going to figure out the. So with the help of this open circuit test, we are going to figure out the we can see that we are going to figure out the copper, or we can say the no load losses. So open circuit test. So we are going to perform this open circuit test. So you can see clearly this is a single phase transformer. So this is the LV winding and this is the HV winding. So the LV winding is going to have a number of turns of N1 and the HV winding is going to have a number of turns of N2. See, for this open circuit test, we are not going to connect any load. So open circuit means we are not going to connect any load. So if this is secondary, then definitely the open circuit means the current drawn here by this load is 0 because it's open circuit. See, in this open circuit test, we are going to give the rated voltage. See, LV winding has small amount of rated voltage when compared to HV winding. So we prefer to give low amount of rated voltage. So therefore we prefer to apply it on the LV side. So HV side is open circuited and LV side we are going to keep a low voltage rating of the. Means we can supply a voltage of rated value of low value. So this is the supply voltage we are going to give. So we are going to connect a voltmeter to figure out the value of this rated voltage. And we are going to connect a wattmeter to measure how much amount of power consumed at this no load condition by this transformer. And also this ammeter is going to measure the value of the no load current I0, and the wattmeter is going to measure the no load power. No load power is also called as the iron losses or core losses. So with the help of wattmeter, we know the rated value of the low voltage winding, and with the help of ammeter we are going to figure out the no load current, and with the help of wattmeter we can measure how much amount of power is absorbed by this transformer at this no load condition. As we can see clearly that this is called as the equivalent circuit diagram of a transformer. As the secondary is open circuited, as I2 is 0, so I dash is also equal to 0. So this is open circuit. Only shunt branch is going to present now, and this is R0 and this is X0. X0 you can go for XM also anything. And this is IW and this is I mu and this is I0 and this is I1. So I1 is also equal to I0 in this condition. So what is the amount of power absorbed at this no load condition is equal to IW square into R0 is equal to V LV rated into I0 into cos phi naught. So these are the two formulas we can apply. Or simply another formula which is VL rated into IW also you can use. Any of these formulas are always correct. Because only the resistor is going to consume the power but not the inductor. Then what is the value of R0? R0 is equal to VLV rated by the IW, and H0 is equal to VLV rated by I mu. So if you know these parameters, with the help of these parameters, we can calculate the R0, we can calculate the H0 also. So this is a diagram of the transformer with respect to the LV side, because we have corrected the test on the LV side. So now I am going to draw the phasor diagram. The phasor diagram is this is the VLV rated and this is the current IW, because they both are in phase because of the resistor, whereas the I mu is going to lag the voltage because it is the inductor. Current is going to lag here. So this is I mu. The vector sum of these two vectors is called as the I0, and the no load power factor, the angle between the supply voltage and the supply current, the angle is called as the power factor. Here it is phi naught is nearly equal to 90 degree. It means that I mu is always higher than the IW. So therefore power factor is nearly equal to 0.2, very low power factor. And you can say IW is equal to I0 into cos phi naught, where I mu is equal to I0 into sin phi naught. And we can say the copper loss is nothing but it is equal to iron loss, is also called as the core loss is also called as the iron loss of core loss. So iron loss is a summation of the hysteresis loss and the eddy current loss. So I have already told you hysteresis loss is equal to eta into Bm to the power of 1/6 into F into volume of core, whereas the eddy current loss is equal to Ke into B max whole square into F square into P square. So you can use some constant P and Q. So P and Q are said to be some constant values. So now we will go for a small special case. Suppose its maximum flux density is constant, then what is going to happen? Then the hysteresis loss is directly proportional to frequency, and the eddy current loss is directly proportional to square of the frequency. So if you remove the proportionality constant, you are going to get the hysteresis loss is equal to A into F, and the eddy current loss is equal to B into F square, where A and B are said to be constants. So what we have done with the help of this open circuit test, we have figured out the sent branch values. So we have figured out the sent branch values, which are the R naught and X naught. So we can easily figure out the value of the R naught and X naught if we done the OC test. So with the help of OC test, we have figured out the value of the R naught and also the X naught, means the sent branch parameters we have calculated with the help of this OC test. So now we are going to done the short circuit test. So why we are going to do the short circuit test means to figure out the series branch parameters. So now we are going to do the short circuit test to figure out the series branch parameters. Short circuit means we have to do the short circuit at the loading side. See, in a short circuit, we send the rated current. We try to send the rated current. For HV winding, the rated current is very less when compared to LV winding. So we try to give a small amount of rated current, but not the high. That is the reason we give the supply for the HV and we short circuit the LV. This is the thing that you always have to remember. So therefore, then this is the supply voltage. So this voltmeter is going to measure the supply voltage, and this is the wattmeter to measure how much amount of power absorbed by this transformer at this condition, and this ammeter is going to measure the rated current of this HV winding. It is a very less, so we need less amount of ammeter range to figure out this current. Then this is HV side and this is the LV side. So here from the previous case I have already told you HV winding has number of turns N2 and LV winding has number of turns N1. So now with the help of voltmeter we figure out the Vs, with the help of ammeter we have figured out the IS rated of HV side, and with the wattmeter we have figured out the amount of power consumed at this condition. So now as we are going to neglect the shunt branch parameters, only we are going to consider this series branch parameters. As it is a short circuit, so here also it is short circuit. Now we are going to prefer to the HV side. We are doing to the HV side. So HV side, this is supply voltage Vs, and this is HV side means here LV means RO1, HV means RO2. So RO2 and XO2. So now this is the ISC rated. So now you can see clearly the amount of short circuit power is equal to ISC HV whole square into R naught of 2, because only resistor is going to consume the power but not the reactor. And Z naught of 2 is equal to Vs by ISC HV. So VSC by ISC HV. So now you can say simply we know PSC, we know ISC. With the help of this we can find the RO2. We know VS, we know IS HV. So with the help of this we know Z naught of 2. Then X naught of 2 is equal to another power Z naught 2 whole square minus R naught 2 whole square. So we know Z2, we know R naught 2. Now we can find the X naught 2. So with the help of the short circuit test we have figured out the R naught of 2 and X naught of 2 with the help of these three basic formulas. So now what is the short circuit power factor? Short circuit power factor, the short circuit test power factor, it is nearly equal to RO2 by Z naught 2. So it is nearly equal to 0.5 to 0.6. It is somewhat higher when compared to the previous case. So you can say the short circuit power factor is higher when compared to the previous OC circuit test. So this nearly from 0.5 to 0.6. So now with the help of OC test we have figured out the shunt branch parameters, and with the help of the AC test we have figured out the series branch parameters. So now I want to redraw the circuit to the LV side. So LV side means R naught X naught. So now as we figured out the R naught 2 and X naught 2 with respect to HV, but I want to do with respect to LV, so therefore I will do some multiplication N1 by N2 whole square into R naught of 2, N1 by N2 whole square into X naught of 2. So this is the equivalent circuit with respect to LV side. So this is the thing that you always have to remember. So in a short circuit test, I am going to assume the source voltage is constant, and when frequency increases, what is going to happen now we are going to see. As you can see clearly, the resistance is independent of the frequency, so R0 is a constant, whereas X02 as the frequency increases, X02 increases because it is directly proportional to frequency. As X02 increases, then definitely Z02 also increases because it is under root over R02 square plus X02 square. As Z02 increases, then the current drawn will decrease because ISC is equal to V by Z0 of 2. VS is constant, Z0 of 2 increases means ISC decreases. Then what is going to happen? Cos phi SC is nothing but R0 of 2 by Z0 of 2. As Z0 of 2 increases, the overall ratio decreases, means the power factor will decrease. So when in a short circuit test, whenever the supply voltage is constant and the frequency increases, R02 is a constant, H02 increases, Z02 increases, ISC decreases, and the power factor will decrease. So losses in a transformer. So now we are going to discuss another concept which is very much important, and the most of the questions are being asked from this topic. So we have to listen, we have to understand this concept in a very detailed manner. Losses in a transformer. Basically, there are two types of losses present in a transformer. I already told this concept, which is variable losses means depends on the load. Variable losses means it is depending on the load, and the constant losses means independent of the load. So we can see for any machine there are two types of losses present: variable loss and constant loss. Variable loss means these losses depending upon the load, and the constant losses means independent of the load. No matter whatever the load, the loss is always constant. So now we will discuss variable losses is also called as the copper losses because they are going depend upon the load. So copper loss is equal to I1 square into R01 is equal to I2 square into R02. So you can go for either circuit referred to primary or circuit referred to secondary. So I1 square into R01 or I2 square into R02. In both the cases, you are going to get the overall copper loss in both the windings. So R naught of 1 is equal to R1 plus N1 by N2 whole square into R2, or R naught of 2 is equal to R2 plus N2 by N1 whole square into R1. So you can see clearly the copper loss is directly proportional to square of the current. Where current is directly proportional to load. As load increases, then definitely current increases because we are going to connect the load in parallel. If we are going to increase the load means we are going to connect the load in parallel. As we are going to increase the load in parallel, the overall resistance will decrease. As the resistance decreases, the current will increase. So we can say current will increase. So therefore, whenever the load increases, the current is increases. So therefore, you take anything. So I is equal to some x times the full load current. So I is equal to some x times the full load current. If you apply full load, then x is equal to 1. Otherwise, if you apply any fraction, then definitely x is equal to x times the I full load. So copper loss is directly proportional to the square of the current, and the current is directly proportional to the load you are applying. So load at the current at any load is equal to x times the current at the full load. Then definitely copper loss at any x load is equal to I square into R naught of 1. I is nothing but x times of I full load current whole square is equal to x square into I full load square into R naught 1 is nothing but x square into full load copper loss. So therefore copper loss at full load. So therefore copper loss at any x load is equal to x square times the copper loss at full load. So copper loss, see the copper loss at any x load, any fraction of x load is equal to x square times the copper loss at the full load, because current at that load is equal to x times the full load current. So I have already told you the copper loss at the full load per unit value is equal to R per unit. So R per unit is equal to copper loss at full load in per unit value. So copper loss at full load per unit value is equal to R per unit. So R per unit is equal to copper loss at full load in per unit value. So R per unit is equal to copper loss at full load in per unit value. So always R1 and R2 are called as a winding resistance, whereas X is called as the fraction of load with respect to full load, or simply we can say X is equal to I current at any load by current at full load, or simply I is equal to current at any load is equal to X times the current at the full load. So we can say the copper loss at any load is equal to, at any X load is equal to X square times the copper loss at full load. Similarly, the R per unit is equal to copper loss at full load at per unit value. So R per unit is equal to copper loss at full load in per unit value. So now we will discuss the iron loss or core loss or constant losses. In a transformer, the variable loss is only copper loss, whereas in a transformer, the constant losses is also called as the iron loss or the core loss. So constant loss is a summation of the hysteresis loss and the eddy current loss. So constant losses in a transformer is a summation of the hysteresis loss and the eddy current losses. These are independent of the load. So now we will discuss something more about this hysteresis losses. Hysteresis losses means, what is the meaning of hysteresis losses means? If you are trying to change the frequency of the magnetic field, so whenever the magnetic field is in the flux in the core is changing its direction, then the dipoles in that magnetic field are also going to rotate. They are going to consume some small amount of energy, so they are going to dissipate small amount of energy, so therefore the core is going to get heated. That is called as hysteresis losses. So hysteresis loss is equal to area of the BH loop into supply frequency. So this is the thing that you always have to remember. So hysteresis losses is equal to area of the BH loop into into supply frequency. So therefore, this is the point that you always have to remember, which is that hysteresis loss is equal to area of the BH loop into frequency. So hysteresis loss is equal to area of the BH loop into frequency. So other formula is hysteresis loss is equal to eta Bm to the power of x into f into volume of core. So hysteresis loss is equal to eta into Bm to the power of x into f into volume of core, where eta is called as the Steinmetz constant and x is called as the Steinmetz exponent. Eta is called as the Steinmetz constant and x is called as the Steinmetz exponent and is equal to 1.6 for silicon or the CRGO, cold roll grain reinforcement, CRGO. And Bm is called as the maximum flux density, and Bm is directly proportional to voltage by frequency, because I have already told you B is nothing but it is equal to E is equal to 4.44 mf Im. So therefore we can say clearly Bm is directly proportional to V by F. So Bm is directly proportional to V by F, where V is called as supply voltage and F is called as supply frequency, where this capital V is called as the volume of the core and the small v is called as the supply voltage. So this is the thing that you always have to remember. So Bm is directly proportional to V by F, the power of 1.6 into F into volume of core. So always hysteresis loss is equal to area of the BH loop into supply frequency, or other formula eta into Bm to the power of x into F into volume of core. Eta is called as the Steinmetz constant and x is eta is called as Steinmetz constant, whereas x is called as the Steinmetz exponent. Its value is equal to 1.6 for the silicon or the CRGO, and Bm is called as the maximum flux density. Always the maximum flux density is directly proportional to voltage by frequency. This capital V is called as the volume of the core and the small v is called as the supply voltage. So this is a formula that you always have to remember while doing the calculation of these hysteresis losses. So now we'll discuss the eddy current losses. See, whenever the flux is going to pass through any core, as core is having some, we can say it is a very combination of huge amount of conductors. So we can say simply that eddy currents are going to produce. Whenever there is a rate of change of flux in a core, we can say eddy currents are going to produce. Because of this eddy currents, a loss is going to produce. That is called as the eddy current loss. So by increasing resistance of core, means by using laminations, we can reduce the eddy current losses. So if you use a high resistive core, or simply if you use the laminations, then definitely you are going to increase the resistance for this current to flow. So therefore the eddy current losses are going to get reduced. The eddy current losses formula is equal to K into Bm square into F square into T square, where T is called as the thickness of the laminations, and thickness of the laminations, and Bm is the maximum flux density, and F is the supply frequency, and K is called as the eddy current loss constant. So this is the formula that you always have to remember. So T is called as thickness of the insulations, Pa is called as the iron loss, and Ph is called as the hysteresis losses, and the P is called as the eddy current loss. So therefore iron loss or the core loss is a solution of the hysteresis loss and the eddy current losses. So now we are going to find what is the iron loss under two cases. So finding iron loss under two cases. So we are going to assume case 1 and case 2. Case 1, when V by F is equal to constant, when the ratio of the voltage by frequency is a constant, then what is going to happen? If V by F is equal to constant, I have already told you Bm is directly proportional to V by F. So whenever the V by F is constant, means Bm is also constant. So I have already told you Ph is equal to eta into Bm to the power of 1.6 into F into volume of core. As Bm is equal to V by F, as V by is a constant, so Ph is directly proportional to F. So Ph is directly proportional to frequency. Whereas P is equal to K into Bm square F square T square, as Bm is directly proportional to V by F, as V by F is constant, so therefore P is directly proportional to F square. So whenever the V by F is a constant, pH is directly proportional to the frequency, and Pe is directly proportional to the square of the frequency. So then net iron loss is equal to summation of the hysteresis loss and the eddy current losses. Suppose if the second case, if V by F is not constant, then if V by F is not constant means the Bm is not constant. Then we will see what is the nature of the pH and Pa. pH is equal to eta Bm to the power of 1.6 into F into volume of 4. Bm is nothing but V by F. So now substitute here above 1.6 F into V. As it is not constant, then write this to do simplification. We are going to get V to the power of 1 by 6 into F to the power of 1 minus 1.6 nothing but minus 0.6. So pH is directly proportional to voltage to the power of 1.6 into frequency to the power of minus 0.6. So pH is directly proportional to voltage to the power of 1.6 into frequency to the power of minus 0.6. Whereas eddy current loss is equal to K into Bm square into F square into T square, as Bm is directly proportional to V by F. So now do a simplification, F square cancels because it is not a constant, so it is independent of frequency. So P is directly proportional to square of the voltage, and the net iron loss or the core loss is the summation of the hysteresis loss and the eddy current loss. So whenever the V by F is not constant, then pH is directly proportional to voltage to the power of 1.6 into frequency to the power of minus 0.6, whereas the eddy current loss is directly proportional to the square of the frequency, and the net iron loss is the summation of the hysteresis loss and the eddy current loss. Then what is going to happen if V by F is a constant? Suppose if V by F is a constant, I've already told you the hysteresis loss is directly proportional to frequency and eddy current loss is directly proportional to square of frequency. So if you remove the proportional to constant and keep a constant, then we are going to get pH is equal to K1 into F and P is equal to K2 into F square. And what is the net iron loss? Summation of hysteresis loss and eddy current loss, which is Pi is equal to K1F plus K2 into F square. And take the frequency, do the division by frequency on this overall total side, we are going to get Pi by F is equal to K1 plus K2 into F. So you can see clearly this is the format of a Y is equal to Mx plus C. So Y is equal to Mx plus C. So Y is nothing but Pi by F and F is nothing but F. So Y is equal to Mx. Mx follows slope. Slope is nothing but K2. The slope of this line is equal to K2. Mx plus C. C is nothing but Y intercept is equal to K1. So this is the graph we are going to get in the format of a straight line with the intercept of K1 and the slope of K2 and the y-axis is Pi by F and is the frequency F. So this is called as this is the graph we are going to get for this whenever the V by F is a constant value. So now we are going to discuss about the efficiency of a transformer. Efficiency of a transformer, now we are going to discuss it detail. So you can see clearly a single phase transformer. The primary winding is of tones of N1, secondary winding is of tones of N2. So for the primary winding we are going to give a supply voltage of plus or minus supply voltage, some voltage we are going to give. For secondary side we are going to connect a load. The input current is I1 and the output current is I2. So this is the induced voltage V1 and induced voltage V2 in the primary and the secondary, where kVA is called as it is the kVA rating of the transformer. So this is the load kVA. So power factor of the load is cos phi 2 and the kVA rating of the load is kVAL. So kVAL is called as the kVA rating of the load and kVA T is called as the kVA rating of the transformer. Then what is the value of X? X is the ratio of the kVA rating of the load by kVA rating of the transformer, or we can say X is the ratio of the load current drawn by the full load current. So full load rated current, or you can say X is the ratio of the current at the particular load by the full load current, or it is the ratio of the kVA of the load by kVA of the transformer. So always X is going to lie between 0 to 1. So always we prefer to keep a kVA rating of the load in between 0 to kVA rating of the load itself, but not exceeding the kVA rating of the transformer. So we try to keep the load kVA between the 0 to the kVA rating of the load. So therefore X is going to lie between 0 to 1. So what is the efficiency of a transformer? So efficiency of a transformer is called as the output power by input power. So output power means the power which is absorbed by the load, and input power means the power which is given to the transformer. So output power means active power. We have to take the output active power by input active power. So therefore output active power is equal to V2 into I2 into cos phi 2. So V2 is the voltage across the, see I am going to neglect all the drops. So therefore V2 into I2 into cos phi 2 by the output power is the output active power is V2 into I2 into cos phi 2 by input active power is nothing but output power plus losses. So therefore output power is V2 I2 cos phi 2 plus what are the losses? There are two losses in the transformer, which are the iron loss and the copper loss. So iron loss plus copper loss at a particular load. So this is the formula of the efficiency of a transformer, which is output active by efficiency of a transformer is equal to output active power by input active power, which is V2 I2 cos phi 2 by V2 I2 cos phi 2 plus Pi plus PCU, iron loss plus copper loss. Suppose at full load what is going to happen? At full load means when the kVA rating of the load is equal to kVA rating of the transformer, it is called as the full load. So therefore what is the value of X? X is equal to 1 because both are equal. So let me assume this both equal to kVA. Then we will see what is going to happen. Now I want to find what is the efficiency of the transformer at the full load condition, which is equal to V2 into here V2 into the full load current I2 full load into cos phi 2 by V2 I2 full load current into cos phi 2 plus Pi plus copper loss at full load is equal to, now V2 into I2 FL, it is called as the kVA rating. So kVA rating of the transformer. So kVA into cos phi 2 by kVA into cos phi 2 plus iron loss plus copper loss at full load, because V2 into I2 full load is called as the kVA rating of the transformer or the kVA rating of the load, both are equal at the full load condition. So this is the efficiency of the transformer at the full load condition. At any other load, if at any other load means the kVA rating of the load is lesser than the kVA rating of the transformer, so X is going to lie between 0 to 1. Then what is going to happen, we'll see. X is called as a fraction of the load. As I have already told you, at any other load, then definitely the current at that load is equal to X times the I2 full load, or we can say the copper loss at any other load is equal to X square times the copper loss at the full load. So I2 is equal to X times the I2 at full load, or copper loss at any load is equal to X square times the copper loss at the full load, where X is called as a fraction of the load. This is called as the efficiency of the transformer at any other load, which is V2 I2 cos phi 2 by V2 I2 cos phi 2 plus iron loss plus copper loss. We are going to find the efficiency of a transformer at any other load, which is V2 I2 cos phi 2 by V2 I2 cos phi 2 plus Pi plus PCU. So this is nothing but I2 is equal to X times the I2 full load. So now I am going to replace I2 as X times the I2 full load. So we are going to get X into V2 into I2 full load cos phi 2 by X into V2 into I2 full load cos phi 2 plus Pi plus copper loss at any other load is equal to X square times the copper loss at full load. But I have already told you V2 into I2 full load is nothing but it's the rating of the transformer. So X into kVA rating of transformer into cos phi 2 by X into kVA rating of transformer into cos phi 2 plus iron loss plus X square full load copper loss. So this is the general formula at any other load. So this is the general formula at any other load. So efficiency of a transformer at any other load is equal to X into kVA rating of transformer into cos phi 2 by X into kVA rating of transformer cos phi 2 plus iron loss plus X square times the copper loss at the full load. So this is the general formula you have to always remember at any other load. So now we will see about the efficiency in the per unit system. So now we will see what is the efficiency in the per unit system. So now the numerator and denominator I will divide by kVA rating of the transformer. For this one I will do the division of kVA rating of a transformer in the numerator and the denominator. Then I will see what I am going to get. So X into kVA rating of transformer into cos phi 2 by kVA rating of the transformer by X into kVA rating of the transformer into cos phi 2 by kVA rating of the transformer plus here Pi plus kVA rating of transformer is nothing but it is a per unit value. So Pi in per unit plus X square into copper loss at full load by kVA rating is nothing but, which is nothing but we are going to get copper loss at full load in per unit value. So here these both are going to get cancelled. Here also both are going to get cancelled. So finally we are going to get the efficiency of the transformer in per unit is nothing but. So finally we are going to get the efficiency in per unit value is equal to X into cos phi 2 by X into cos phi 2 plus iron loss at in per unit value plus X square times the copper loss at full load in per unit value. So this is the efficiency of the transformer in the per unit values. So if you know the per unit values, just substitute in this formula to get the efficiency of transformer at any other load condition. See, at maximum efficiency what is going to happen? At maximum efficiency iron loss is equal to copper loss. So iron loss is equal to copper loss. So iron loss is equal to copper loss means this value is equal to this value. So I am going to replace this value as iron loss in per unit. So if you substitute here, we are going to get X into cos phi 2 by X into cos phi 2 plus 2 times of iron loss in per unit value. So therefore this is the formula you are going to get. Then what is the value of X? X is equal to under root over iron loss in per unit by copper loss in full load in per unit value. So what is the value of X? X is the under root over iron loss in per unit by copper loss at full load in per unit value is equal to under root over iron loss in per unit by, as I have already told you, the copper loss at full load in per unit value is equal to R per unit. So therefore under root over iron loss in per unit by R per unit. So therefore this is the formulas that we have to remember for maximum efficiency. If you know the per unit values, just substitute here, you are going to get the maximum efficiency. See, at what fraction of load we get the maximum efficiency. So if you want to find at what fraction of load we are going to get the maximum efficiency from this for this transformer, means as I've already told you, the general expression of the transform, the efficiency of a transformer is equal to x into kV rating of transformer into cos phi 2 by x into kV rating of transformer into cos phi 2 plus iron loss plus iron loss plus x square into copper loss at full load. So now what I am going to basically, I am going to divide the numerator and denominator by value of x. So if I do the division by x on numerator and denominator, I am going to get this equation, which is efficiency is equal to kV rating of transformer into cos phi 2 by kV rating of transformer into cos phi 2 plus pi by x plus x into copper loss in per unit. Definitely, if you want to find what is the maximum efficiency for a particular value of fraction of load, then derivative at the maximum efficiency at that point should be equal to 0. So d efficiency by dx is equal to 0, means the derivative of the function at the maximum point should be always equal to 0. So therefore, if you do the derivative of this one, we are going to get in this manner. So therefore, d by dx of pi by x plus x into copper loss at full load is equal to 0. So if you do the derivative of this function, finally we are going to get iron loss is equal to copper loss. So iron loss is equal to copper loss, we are going to get iron loss pi is equal to copper loss at that load is equal to x square times the copper loss at full load. So therefore x is equal to under root over iron loss, x is equal to under root over iron loss by copper loss at that full load. Then we get that I've already told you x is the ratio of the kV rating of the load by kV rating of the load of the transformer. So x is equal to ratio of the kV rating of the load by kV rating of the transformer. So kV rating of the load is equal to x times the kV rating of the transformer. So substitute the value of x here, we are going to get, so this is the kV rating of the load. For this we are going to get the maximum efficiency. So this is the, if you substitute the value of x here, this value if you substitute here, we are going to get, this is the kV rating of the load at which we are going to get the maximum efficiency. As I've already told you, iron loss is equal to copper loss is equal to x square times the copper loss at full load. At this point we are going to get the maximum efficiency. So iron loss and copper loss are equal at maximum efficiency. This is the point that you always have to remember. So iron loss is equal to copper loss at the maximum efficiency. So x is equal to under root over iron loss by copper loss at full load is equal to, if you want in terms of per unit, just do the ratio under root over iron loss in per unit by copper loss in full load per unit. I have already told you copper loss at full load in per unit value is equal to R per unit. So then what is the value of the Z per unit? Z per unit is equal to under root over R per unit whole square plus X per unit whole square. So if you take the per unit values, we are going to get the per unit value. So Z per unit is equal to under root over R per unit whole square plus X per unit whole square. Then what is the maximum efficiency? So maximum efficiency is equal to x into kV rating of transformer into cos phi 2 by x into kV rating of transformer into cos phi 2 plus, I have already told you, iron loss is equal to copper loss at that instant of that load. So therefore 2 times of pi, and x is equal to under root over iron loss by copper loss at full load, or simply in terms of per unit, under root over iron loss in per unit by copper loss in full load at per unit. Whereas copper loss at full load per unit value is equal to R per unit. So efficiency is nothing but percentage of efficiency is equal to output active power by input active power into 100. And I have already told you iron loss, WI is called as a full load iron loss from OC test. From OC test we are going to get the iron loss or the core loss, which are the constant losses. Whereas the copper loss are called as a full load copper loss. Here from SC test we are going to get the full load copper loss is equal to I full load square into R01. So WI is equal to I1 square into R01. So therefore iron loss is equal to copper loss at the maximum efficiency. So from this we can say I1 is equal to under root over WI by R01. So therefore for this current maximum efficiency occurs. So this is the current at which maximum efficiency is going to get occur. So therefore iron loss is equal to copper losses. So iron loss is equal to WI is equal to I1 square R01. So I1 is equal to under root over WI by R0 of 1. So for this current only we are going to get the maximum efficiency. As I've already told you, at maximum efficiency the current is equal to X times the full load current. So if you substitute here we are going to get WI is equal to X square times the I full load current whole square into R01. I full load whole square into R naught 1 is called as a full load copper loss. So this is called as a full load copper loss. So therefore X is equal to under root over iron loss by copper loss at the full load. So X is equal to under root over iron loss by copper loss at the full load. Then what is the load at maximum efficiency? What is the rating of the load at maximum efficiency is equal to just X times the rating of the transformer. So therefore the load at maximum efficiency, or the rating of the load at maximum efficiency is equal to, which is X is nothing but under root over iron loss by copper loss at full load. So therefore into this value, which is the KVA rating of the transformer or the full load. So therefore we are going to get, we can say the load KVA at maximum efficiency is equal to full load rating of the transformer or full load rating of the load into under root over iron loss by copper loss at full load is equal to X times the rating of the transformer or the rating of the full load. So you can go for any of these, you are going to get the same result. So now condition for maximum efficiency in a transformer. So what is the condition for maximum efficiency in a transformer? The condition for maximum efficiency in a transformer, I have already told you that the iron loss is equal to copper loss. So iron loss is equal to copper loss at that maximum efficiency. So therefore, what is the copper loss at full load is equal to I1 full load whole square into R naught 1. So do the division of these two things. So we are going to get in this manner. If you do the division of these two things, we are going to get I1 full load is equal to under root over Wi by copper loss at full load. So therefore, now do the multiplication of full load on both the sides. So full load is nothing but V1 into I full load. So I full load and I full load are going to get cancelled. So I full load is nothing but V1 into I full load. So I full load cancels. So we are going to get, this is the load at which the max efficiency is going to occur is equal to full load rating or the rating of the transformer into under root over iron loss by copper loss at full load. So therefore WI is called as iron loss and WCFL is called as the full load copper loss. Full load means the unit is equal to KVA. It is a full load or the maximum rating of the transformer. So therefore we can say this is the load KVA at which maximum efficiency is going to occur, which is equal to X times the rating of the transformer, or simply X is equal to under root over Wi by copper loss at full load into the rating of the transformer or the full load. So efficiency of a transformer at any fraction of load. So efficiency of transformer at any fraction of load, now we are going to see efficiency is equal to output active power by input active power. So therefore we are going to get finally efficiency of a transformer is equal to X times the full load KVA into power factor by X into full load KVA into power factor plus iron loss plus X square times the full load copper loss. So if you want percentage efficiency means multiply by 100. So efficiency into 100. So X value is going to lie between 0 to 1. All these things I have already told you. So now if you draw the graph between the efficiency of a transformer and the value of X, if you draw the equation with respect to efficiency and the X for a given value of power factor, you are going to get like this. So at maximum efficiency is nothing but, so at this point the maximum efficiency is going to get occur, which is equal to X is equal to under root over iron loss by copper loss at full load. So if you increase the power factor, this graph is going to shift upward. So therefore, but the maximum point is always same. So at this point the maximum efficiency is going to get occur, but if you increase the power factor of the load, this graph is going to increase further and further, means the efficiency is going to increase at the maximum efficiency. The maximum efficiency is going to get increased more and more if you increase the power factor, because this efficiency is a function of two parameters, which are the X and also the power factor. So for a given graph, we are going to assume the power factor is constant. Again, for this graph, we have increased the power factor and it is a constant for this overall graph. Again, we have increased the power factor. Again, this is like this. So we can say that the efficiency of a transformer is a function of the fraction of the load and also the power factor. So if you increase the power factor, this graph is going to get shifted higher and higher, but the occurrence of the maximum efficiency is always fixed. This value is always fixed, which is equal to under root over iron loss by copper loss at full load. So if you increase more than its rating, if you keep a load more than its rating of transformer, then the efficiency goes on decreases. The efficiency of the transformer goes on decreases. It is called as the overloading of transformer. So if you keep more and more load when compared to its rating, then we can say the efficiency goes on decreases. So if you keep more and more load more than its rating of transformer, then its efficiency is going to get decrease. So now we will discuss about the voltage regulation of the transformer. This is a very new concept. So voltage regulation of the transformer. Suppose I am going to consider only the secondary part of the transformer. Only the secondary part I am going to consider. So I will see basically I have transformed all the primary to the secondary. So now I am going to get a voltage of E2. Here I am going to get a voltage of V2. E2. This voltage is called as E2, and this is R0 of 2, and this is X0 of 2, and this is the load we are going to get. So basically I have transformed the total primary into secondary. So this is called as E2, R0 of 2, X0 of 2, and this is the load we are going to keep. The load is basically of lagging load with a power factor of cos phi, and this is the load voltage which is plus or minus V2, and the load current is I2. So now I want to apply the KVL in this secondary loop. So we are going to get E2 bar is equal to V2 bar plus I2 bar into R0 of 2 plus J X0 of 2. So E2 bar is equal to V2 bar plus I2 into R0 of 2 plus J X0 of 2. So this is the vector, this is the equation of the KVL in this loop we are going to get. So now I will draw the phasor diagram. So now I will draw the phasor diagram for this equation. So you can see clearly that now this is the terminal voltage V2. As I have already told you, the load is a lagging power factor. So therefore the load in current is going, the load current I2 is going to lag the load voltage by a small amount of power factor angle phi. But you can see clearly I2 and R0 of 2 are in phase. So I2 into R0 of 2, the voltage across the resistor and the current are in always phase. So therefore this is called as the I2 into R0 of 2, whereas the voltage and current across the inductor are going to have a perpendicular degrees, 90 degrees. So current is going to lag the voltage by 90 degrees in an inductor. So therefore this is the voltage which is nothing but I2 into X0 of 2. So if we add these three vectors, we are going to get the overall vector E2. So therefore this is the vector E2 we are going to get. So this is the vector we are going to get. So basically suppose if I take a length of O2 E2 bar, if I take an arc of length 0 to E2, and if I make an arc, then it is going to cut a point D if you extend this line, straight line at a point D. So you can see clearly that if you make an arc with O2 as a radius with a compass, then we are going to get at a point D we are going to get here. So then what I am going to do basically here is basically now I am going to do some small amount of approximation. So this is 90 degree. If this is 90 degree, then this is phi, then this will be 90 minus phi. So this is also 90 minus phi. So now let me do small amount of analysis or approximations. So OD is nearly equal to OC. See, I am going to draw a straight line from this point up to this point. So if I draw a straight line from E to this line, we are going to get a point C. So if you draw a straight perpendicular line from from this point, you are going to get a point C. So now I am going to do small amount of approximation. So you can see clearly AB is equal to I2 R0 of 2 cos phi, whereas BC is equal to, so this angle is pi minus 90 minus pi. So therefore simply we can say that this total length is nothing but BC length is equal to I2 X0 of 2 into cos of 90 minus phi. Cos of 90 minus phi is nothing but sin phi. So this is the thing we can say that OD is now nearly equal to OC. So therefore OD is nearly equal to OC, but OD is equal to OE length. So therefore this is called as the E2 length. So therefore this total length is E2. So simply we can say that E2 is equal to V2 plus I2 R0 of 2 cos phi plus I2 X0 of 2 cos of 90 minus phi is nothing but sin phi. So this is the algebraic values only, not the vector values or the phase values. These are only the algebraic values. So E2 is equal to V2 plus I2 R0 of 2 cos phi plus I2 X0 of 2 sin phi. So this is the equation we are going to get. So now if I take V2 to the left side LHS, we are going to get E2 minus V2. So E2 minus V2 is equal to I2 into R naught of 2 cos phi plus I2 into X naught of 2 sin phi. If you take I2 as a common, we are going to get I2 into R naught of 2 cos phi plus XO2 into sin phi. So we can say E2 minus V2 is nothing but which is the voltage drop across the internal impedance. So E2 minus V2 is called as the voltage drop across the internal impedance, and VR is called as the voltage regulation. Suppose I2 is equal to current at any given load. So current at any given load is equal to X times the full load current. So X times the I2 full load. So current at any given load is equal to X times the full load current. So I2 is equal to current at any load is equal to X times the I2 full load current. So therefore, if you want to find what is the voltage drop at any other full load, at any other load, then we can write this expression E2 minus V2 is equal to, just replace I2 is equal to X times of I2 full load. So we are going to get X times of I2 full load into R naught of 2 cos phi plus X naught of 2 sin phi. So this is the equation we are going to get. So now what is the voltage regulation? Voltage regulation is equal to voltage drop across the impedance by the total no load voltage, or simply we can say no load voltage minus load voltage by no load voltage. So listen carefully, voltage regulation is equal to no load voltage minus load voltage by no load voltage. No load voltage is just remove the load, the voltage is nothing but E2. If you keep a load, the voltage across the load is E2 by no load voltage means just remove the load, the voltage across the no load condition is nothing but E2. So no load voltage minus load voltage by no load voltage. So this is called as the voltage drop across the internal impedance by the no load voltage E2 is equal to, as we know, E2 minus V2 is equal to X into I2 FL into R naught of 2 cos phi plus X naught of 2 sin phi by E2. So voltage regulation is equal to E2 minus V2 by E2. So now what I am going to basically, I am going to take this E2 FL to the downward. So we are going to get like this, X into R naught of 2 cos phi plus X naught of 2 into sin phi by E2 by I2 FL. E2 by I2 FL is called as the base voltage by base current is called as the base impedance. So base voltage by base current is called as the base impedance. It is equal to ZB. So now I am going to do the division into both this part and this part. So voltage regulation is equal to X into R naught of 2 by ZB into cos phi plus X naught of 2 by ZB into sin phi. So R naught of 2 by ZB is nothing but actual value by base value is equal to per unit value. So R per unit into cos phi plus X naught of 2 by ZB, actual value by base value is equal to per unit value, X per unit into sin phi. So this is called as the voltage regulation at any load. So this is the voltage regulation formula at any other load. So voltage regulation, if you want percentage voltage regulation, just do the multiplication by 100. So voltage regulation is equal to X into R per unit into cos phi plus X per unit into sin phi. So voltage regulation is equal to X into R per unit cos phi plus X into X per unit into sin phi. So voltage regulation is equal to X of R per unit into cos phi plus X per unit into sin phi. This is called as the voltage regulation at any load condition. So now we will discuss about the general formula. What is the general formula we are going to discuss? The general formula I have already told you, the voltage regulation is equal to X into R per unit cos phi plus or minus X per unit sin phi. Here plus is for the lagging load and minus is for the leading load. So whenever you keep a lagging load, then we have to go for the sign of positive. If it is a leading load, then go for the sign negative. So VR is called the voltage regulation at any load. So therefore, voltage regulation at any load is equal to X times the voltage regulation at full load. At full load means substitute X is equal to 1. So you are going to get this term. So therefore, you can say that voltage regulation at any load is equal to X times the voltage regulation at full load. So this is a very important point that you always have to remember. So voltage regulation is equal to X into R per unit cos phi plus or minus X per unit sin phi. Plus is for the lagging load and minus is for the leading load. So VR is called as a voltage regulation at any load. So voltage regulation at any load is equal to X into voltage regulation at full load, because at full load X is equal to 1 we are going to get. So now we are going to discuss the maximum voltage regulation. So when we are going to get the maximum voltage regulation, maximum means it is going to occur at the lagging load. Lagging load means we have to go for the positive sign. So therefore, the maximum voltage regulation is going to occur at the lagging load because we are going to get a positive sign. So therefore, now if you want to do the differentiation with respect to phi, so d by d phi of voltage regulation is equal to 0. then simply we are going to get like this. So therefore, if you do the simplification, we are going to get r per unit into differentiation of cos phi is nothing but minus sin phi plus x per unit into differentiation of sin pi is cos phi. So therefore, if you do the simplification, if you do the rearrangement, then we are going to get finally that tan phi is equal to x per unit by r per unit, or simply x naught of 2 by r naught of 2, because x per unit is equal to x naught of 2 by z base and r per unit is equal to r naught of 2 by z base. So z base cancels, we are going to get x naught of 2 by r naught of 2. So we can say this is the power factor angle. Phi is equal to tan inverse of x naught of 2 by r naught of 2. At this power factor angle, we are going to get the maximum voltage regulation. Maximum voltage regulation means maximum voltage drop across the internal impedance. So maximum voltage drop across the internal impedance. So voltage regulation is going to tell you how much amount of more is the voltage regulation, more is the voltage drop across the internal impedance. So more is the voltage regulation means more is the voltage drop across the internal impedance. That is the significance of the voltage regulation. So tan phi is equal to x per unit by r per unit is equal to x naught of 2 by r naught of 2. So basically at the lagging load, we are going to get a positive sign and do the differentiation with respect to phi for this voltage regulation. We are going to get, finally you are going to get, if you equal to 0, we are going to get, this is the value we are going to get. So this is the phi, this is r naught of 2 and this is the x naught of 2. So therefore phi is equal to tan inverse of x naught of 2 by phi r naught of 2. At this lagging load, we are going to get the maximum voltage regulation. So this is the r naught of 2, this is the x naught of 2 and this is the angle phi. So tan phi is equal to x naught of 2 by r naught of 2. So phi is equal to tan inverse of x naught of 2 by r naught of 2. At this power factor, lagging power factor angle, we are going to get the maximum voltage regulation. So now zero voltage regulation. So what is the meaning of the zero voltage regulation? Zero voltage regulation we are going to get occur if you go for the leading load, then only we are going to get negative. Then if you equate the voltage regulation is equal to 0, it is going to occur at the leading load, because we are going to get a negative sign in the voltage regulation. And if you equate the voltage regulation to 0, the minimum value is 0. So therefore 0 voltage regulation we are going to get here. So therefore voltage regulation is equal to 0. So if we equate to 0, then finally we are going to get tan phi is equal to r per unit by x per unit. R per unit is equal to r naught of 2 by z base and x per unit is equal to x naught of 2 by z base. We are going to get r naught of 2 by x naught of 2. So if you shift the angle to this side, if you shift, previously you have made the angle phi here, but now shift the angle to here. So we are going to get, this is r naught of 2, x naught of 2. So tan phi is equal to r naught of 2 by x naught of 2, or simply r per unit by x per unit. So this is the angle. Phi is equal to power factor angle is equal to tan inverse of r naught of 2 by x naught of 2. At this leading power factor angle, we are going to get the zero voltage regulation. So if you want maximum voltage regulation, if you want the maximum voltage regulation means the power factor angle is equal to tan inverse of x naught of 2 by r naught of 2 at the lagging power factor angle. Whereas if you want the zero voltage regulation, then definitely you are going to get the power factor angle is equal to tan inverse of r naught of 2 by x naught of 2. At this leading power factor angle, you are going to get the zero voltage regulation. So now basically now I am going to draw the plot diagram with respect to voltage regulation and the power factor angle. So this RHS I am going to consider it as the lagging load, and this LHS I am going to consider it as the leading load. So I have already told you, in the lagging load, for a particular value of phi, we are going to get the maximum voltage regulation. So this is the, at this angle we are going to get the maximum voltage regulation. More is the voltage regulation, more is the voltage drop across the internal impedance. So that power factor angle is called tan inverse of x naught of 2 by r naught of 2, or x per unit by r per unit. At this lagging power factor angle, you are going to get the maximum voltage regulation. Whereas you are going to get the zero voltage regulation. You are going to get the zero voltage regulation at a power factor angle, which is phi is equal to tan inverse of r naught of 2 by x naught of 2, or r per unit by x per unit. At this leading power factor angle, you are going to get the zero voltage regulation. So now you can see clearly, for lagging loads, always the voltage regulation is always positive. Always the voltage regulation is always positive, means the load voltage is always lesser than the no load voltage. So listen carefully. For lagging loads, always the load voltage is always lesser than the no load voltage. Means V2 is always lesser than E2. That is the reason always the voltage regulation is always positive for the lagging loads. Whereas for leading loads, you can get three types of cases, which is load voltage can be greater than the no load voltage, the load voltage can be equal to no load voltage, or the load voltage can be lesser than the no load voltage. These three cases are possible. That is the reason the voltage regulation is positive, zero, and also negative. All these three cases are going to possible only for the leading loads. So therefore we can say clearly that is the reason for lagging power factor angles the voltage regulation is always positive, whereas for leading power factor the voltage regulation is a positive, it is a zero, and it also negative. So this is a very important point that you always have to remember. So whenever the E2 is greater than V2, then only the voltage regulation is positive, and whenever the E2 is equal to V2, the voltage regulation is zero, and whenever the E2 is lesser than V2, then we can say the voltage regulation is negative. So this is the thing. All these three things are going to possible only in the leading load, but only voltage regulation is always positive in the lagging load. So this is a very important point that you always have to remember. So now X is called as the I've already told you X is called as the fraction of load, which is the ratio of the actual load current by the full load current. So therefore actual load current by full load current, which is I2 by I2FL, is equal to, or we can go for another thing which is called as the kVA rating of the load by the kVA rating of the transformer. So X is called as the actual load current by the full load current, or the ratio of the load kVA by the load means a transformer kVA. So therefore SL is called as a load kVA and ST is called as the transformer kVA. It's a very important point. Now we are going to discuss about the parallel operation at transformer. So parallel operation in transformer now we are going to discuss. Suppose there are two transformers, transformer A and the transformer B. So these are the two transformers, transformer A and transformer B. So we are going to connect them in the parallel. So we are going to connect them in parallel means here you can see clearly. So this is like this. This is a dotted term and this is also dotted. So two same dots we are going to connect. So same two dots we are going to connect. So here basically there will be a dot here. Here there will be a dot here. So we are going to connect the same polarities of the dot, and the remaining terms, the remaining term we are going to connect these 2 points. Similarly here also there will be dotted point. Here also there is dotted point. So same dots we are going to connect. The remaining things are going to connect like this. So this connection, this value we are going to give to A, this terminals we are going to give a load. So now this load is shared by both the transformer A and also the transformer B. So now overall equivalent internal impedance of this transformer A referred to secondary is ZA. Similarly, the overall equivalent impedance referred to secondary of this transformer B is ZB. So ZA and ZB for the transformer A and transformer B. So this transformer A is going to give a current of IA and this transformer B is going to give a current of IB, and this is the load current. So load current is shared by both the transformer A and the transformer B, and this is the load voltage VL and the supply voltage is V1. So basically parallel operation of transformer means we are going to share the load with respect to two transformers. Suppose if one transformer is gone, then this load can be shared by the remaining transformer itself. So therefore always the load is always going to get the continuous power even if one transformer gets failure. So load will always get the power irrespective of the failure of the one of the transformer. This is the usual of the parallel operation. So load is always going to get the power even if one of the transformer got failure. So why parallel operation? Why we are going to choose the parallel operation? See, load sharing, this increases the power sharing capacity. So basically with the help of two transformers connecting in parallel, we are going to sharing the load. It increases the power sharing capacity, means more power we can supply to a load. So with the help of this we can supply more amount of power to the load. So load sharing, this increases the power sharing capacity. So therefore, see, with the help of these parallel transformers, we can increase the power sharing capacity to the load. So with the help of these two transformers connecting in parallel, we are going to share the power sharing capacity to the load. So load sharing, this increases the power sharing capacity of the transformers and the continuous flow of power during fault in one transformer. So you can see clearly continuous flow of power during fault at one transformer. Even if one transformer got failure, then the remaining transformer is going to give the power to the load. So load is always going to get the power irrespective of the failure of the any one of the transformer. So because of the other transformer, so continuous flow of power during the fault in one transformer because of the other transformer. As one transformer got failure, but the other transformer is going to give the supply to the load always. So what are the necessary conditions that you should always check before doing the parallel connection of the transformers? You should be always checking some conditions, the necessary conditions. If these conditions are satisfied, then only you should operate the transformer parallelly. Otherwise, you don't have to operate the transformer in parallel. The necessary conditions are these are called as the compulsory conditions. These conditions should be satisfied before you go for the parallel operation of transformers. You have to check it before you connect the load for this parallel operation of these transformers. One is same voltage ratings. The voltage ratings of the two transformers should be always same. The voltage ratings of the transformer A and the transformer B should be always same. It's the first necessary condition. And the same polarity terminals are connected for the primary side and for also the secondary side. Same polarity terminals are always connected, and the same phase sequence in three-phase transformer. See, same phase sequence in three-phase transformer. If the transformer is a star to delta, then transformer B should also be star to delta connection. And same phase shift in three-phase transformer. So similarly, again, in a type of three-phase star delta, there is again phase sequence, phase shift, same phase shift should be there. So therefore, you can say these are the four necessary conditions you should always check before connecting the load to these parallel transformers. One is they should have the same voltage ratings. Same polarity terminals are connected for the primary and also the secondary, and the same phase sequence in the three-phase transformers, and also same phase shift in a three-phase transformer. In a three-phase transformer, the connections and also the phase shift are going to present in a connection. The phase shift should be always same. If it is a star delta 1 degree, it means the another transformer should also be star delta 1 am, 1 pm or 1 am. So therefore we can say that simply. So listen carefully. Same voltage ratings, same polarity terminals are connected for primary and secondary, same phase sequence in three-phase transformers, and same phase shift in the three-phase transformers. Then these are the conditions you should always satisfy. These are the four necessary conditions that you should always satisfy before connecting a load to the parallel operation of transformers. I am repeating the necessary conditions. Same voltage ratings for the transformer A and transformer B. Same polarity terminals are connected for the primary and the secondary of the transformer A and transformer B. Same phase sequence in the three-phase transformer, and the same phase shift in the three-phase transformer. Same phase sequence and the same phase shift. This is a very much necessary condition for the operation of the three-phase transformers in a parallel condition. So now desirable condition. So desirable condition means it is not necessary condition. Desirable condition but not necessary for parallel operation. It is not a necessary condition. It is a desirable condition but not necessary condition for parallel operation, which is the load sharing by transformer A by load sharing by transformer B, which is equal to SA by SB is equal to KVA rating of the transformer A by KVA rating of the transformer B. The load sharing by transformer A by load sharing of transformer B is called as the SA by SB is equal to KVA rating of the transformer A by KVA rating of the transformer B. So now another important point is here, this internal impedance, the ratio should be the internal impedance angle should be always, this is a desirable condition but not a necessary condition. The internal impedance angle should be equal. So XA by RA is equal to XC by RB. So therefore phi A is equal to tan inverse of XA by RA and phi B is equal to tan inverse of XC by RB. Their angles are equal. So we can say it is a desirable condition but not necessary condition. So we can say that the load sharing by transformer A is equal to SA by the load sharing by transformer B is equal to SB is equal to KVA rating of the transformer A by KVA rating of the transformer B, and the XA by RA is equal to XC by RB, internal impedance of transformer and transformer B. So phi A is equal to tan inverse of XA by RA and phi B is equal to tan inverse of XC by RB. Their angles are equal for desirable condition but not the necessary condition. These two are the desirable conditions but not the necessary conditions for operation of parallel the operation of transformers. So now we are going to basically analyze this circuit. So now we are going to analyze this parallel operation of transformers. So you can see clearly that these two transformers are connected in parallel. So we are going to see from the secondary side. Secondary side for the A transformer, for transformer A, it is going to have small amount of voltage EA with the impedance of ZA. Similarly, this transformer B is going to have some voltage of EB with a impedance in series of ZB. These two are going to connect in this fashion to give they are going to connect to the load. So these are going to connect in this manner. So therefore they are going to give power to this load. Load is having a complex, we can say SL is called as the kV rating of the load and ZL is called as the impedance of the load, and V is the voltage across the load and IL is the current in the load. So V is called as the voltage across the load and IL is the current across the load, and the SL is called as the rating of the load and ZL is called as the impedance of the load. IA is the current which is generated by the transformer A and IB is the current which is generated by the transformer B. I have already told you necessary condition always EA is equal to EB is equal to E. I have already told you in a necessary condition the voltage ratings of the two transformers should be always same. So therefore EA is equal to EB is equal to always E. So if they are not equal means a leakage current is going to pass between the transformer A and transformer B. It is not a good thing because of that heat is going to get generated. So if you want to remove that one, then we can say that there is no leakage currents between this transformer A and transformer B if you go for the same voltage ratings. So necessary condition which is EA is equal to EB is equal to E. So now if you are going to apply the Thevenin circuit, if you go for the applying Thevenin circuits across these two terminals, we can see simply as of both of same voltage, then the current between them is equal to 0. So therefore the Thevenin voltage is equal to E, and if you want the Thevenin impedance, just to the short circuit of these voltages, the Thevenin impedance is parallel combination of ZA and ZB. So therefore now I am going to write in terms of the Thevenin equivalent circuit for this complex circuit. So this is the Thevenin equivalent circuit. So this is the Thevenin voltage E and Thevenin impedance is the parallel combination of the ZA and ZB. In the previous case, the current in ZA is IA and the current in ZB is IB. So this is IA and this is IB, and this is the load. Load having a load impedance of ZL, the load voltage is V and the load current is IL. So now if you apply the basic, so now basically now if you apply that current rule, or we can say the current rule at this junction, if you apply the current division rule at this junction, you can see IA is equal to IL into ZB by ZA plus ZB. So IA is equal to IL into ZB by ZA plus ZB, and simply IB is equal to IL into ZA by ZB plus ZB. So this is basically current division principle. So IA is equal to IL into ZB by ZA plus ZB. Similarly IB is equal to IL into ZA by ZA plus ZB. So this is a basically current division principle. Then what is the load kVA? The load kVA SL is equal to V into IL conjugate. So V into IL conjugate is equal to, as IL is nothing but IL is equal to IA plus IB. So IA plus IB whole conjugate is equal to IA conjugate plus IB conjugate. So if you take V inside, we are going to get V into IA conjugate plus V into IB conjugate. So therefore SL is equal to V into IL conjugate is equal to V into IA conjugate plus V into IB conjugate. Then V into IA conjugate is called as the complex power which is sent by the transformer A. So SA is equal to V into IA conjugate means this is the complex power which is sent by the transformer A, or this much amount of kVA is sent by the transformer A, or simply we can say this much amount of kVA which is shared by the transformer A, which is V into IA conjugate. So now, but I have already told you what is the value of IA. IA is equal to IL into ZB by ZA plus ZB. Take the whole conjugate, then we are going to get V into IL conjugate into ZB by ZA plus ZB whole conjugate. So V into IL conjugate is nothing but SL. So SL into ZB by ZA plus ZB whole conjugate. Similarly, SB is equal to V into IB conjugate. So this is the kVA shared by the transformer B is equal to IB conjugate. IB is nothing but IL into ZA by ZA plus ZB. Take the whole conjugate, we are going to get simply V into IL conjugate into ZA by ZA plus ZB whole conjugate. So V into IL conjugate is nothing but SL. So SL into ZA by ZA plus ZB whole conjugate. So this is the amount of kVA should be the transformer A, and this is the amount of kVA should by the transformer B. Then what is the net kVA? Net kVA, the kVA of the load is equal to kVA by transformer A plus kVA by transformer B. Basically all these things are vector quantities. These are all vector quantities. So SL is equal to SA plus SB. So if you go for just magnitude values, then mod of SA by mod of SB, it is nothing but simply we are going to get mod of ZB by mod of ZA. So if you do the division of these two things, then simply we are going to get SA by SB is equal to ZB by ZA whole conjugate. But if you are taking only the magnitude values, then mod of SA by mod of SB is equal to mod of ZB by mod of ZA. So you can see clearly that the load sharing by transformer A is inversely proportional to its leakage impedance or internal impedance. So less is the internal impedance, means it is going to share the huge amount of kVA. So this is the point that you always have to remember. So less is the internal impedance or less is the leakage impedance of a transformer, more is the sharing by this, more is the amount of load shared by the transformer. So less is the internal impedance or leakage impedance, then the transformer is going to share the huge amount of load. So therefore this is the thing that you always have to remember, because both are inversely proportional. So you can see clearly here. So now for lagging load we are going to see one condition. So for lagging load, the voltage I am going to assume, the voltage across the load is equal to mod V at an angle of 0 degree. So current is going to lag. So current is equal to mod of I into at an angle of minus pi, because current is going to lag the voltage. Now what is the complex power of the load? S is equal to V into I conjugate. These are vector quantities. So V into I conjugate is nothing but, if you do this one, we are going to get mod V into mod I into, we can say plus 5 at an angle of plus 5. So at an angle of plus 5 we are going to get. Then what is mod V into mod I? This is called as the complex power. So complex power is the ratio of the P by active power by cos phi. So therefore, as I already told you, cos phi is equal to P by mod S. So mod S is equal to P by cos phi. Cos phi is equal to P by mod S. So mod S is equal to P by cos phi. So P by cos phi into at an angle of plus phi. So therefore this is the thing that you always have to remember. So therefore this is the load kVA, or we can say the load kVA in terms of the power factor, active power, and the at an angle of power factor plus phi. So therefore S is equal to P by cos phi into at an angle of plus phi degree. So therefore S is equal to P by cos phi into at an angle of plus phi for lagging load. For leading load, what is going to happen? For leading load, suppose if I take the supply, the voltage across the load as reference, V is equal to mod V at an angle of 0, then the current is going to lead it, the voltage. So I is equal to mod I at an angle of 5. Then what is the complex power? VI conjugate. V is nothing but mod V at an angle 0. I is nothing but mod I at an angle of 5 whole conjugate. So we are going to get mod V into mod I into at an angle of minus pi. So mod V into mod I is nothing but simply I have already told you P by cos phi. So P by cos phi into at an angle of minus pi. So this is the complex power of a leading load, which is P by cos phi into at an angle of minus pi. So this is called the complex power of a leading load. So complex power of a leading load in its representation in terms of the complex power. So you have to use these things to simplify the questions. For a load proportional to their kVA rating, per unit impedance on the individual base must be equal. To share a load proportional to their kVA rating, the per unit impedance on the individual base must be equal. So this is not a necessary condition. I have already told you these are called as the desirable conditions. Only 4 things are the necessary conditions. Remaining everything is a desirable condition. So to share a load proportional to their kVA ratings, per unit impedance on the individual base must be equal. So now we'll see what will happen here. Suppose the transformer A per unit value is equal to transformer B impedance per unit value. So to share a load proportional to the kVA readings, per unit impedance on their individual base must be equal. It means that ZA per unit is equal to ZB per unit. These are just desirable conditions but not necessary condition. So I've already told you mod of SA by mod of SB is equal to mod of ZB by mod of ZA. All these things I've already told you. It is equal to kVA reading of transformer A by kVA reading of the transformer B. See, now to share a load which is proportional to the kVA rating, the per unit impedance on the individual base must be equal. Now we'll see what will happen. So mod of SA by mod of SB is equal to mod of ZB by mod of ZA is equal to KVA by transformer A by KVA of transformer B. Then do the cross multiplication. We are going to get mod SA into mod ZA is equal to mod SB into mod ZB. Then do the division by V base square on both sides. Then we are going to get V base square on both sides. We are going to do this one. Then we are going to get like this. So I have already told you base voltage is same for both the things because of equal voltage ratings. So same voltage, it is nothing but that ZA per unit is equal to ZB per unit. So this is called as ZA per unit and this is called as the ZB per unit. So therefore, if you see clearly, if you want to share a load proportional to the KVA ratings, the per unit impedance on the individual base must be always equal. Actually here you have to do this cross multiplication. Actually you have to do not this one. You have to do the cross multiplication of this one. Then we are going to get KVA of transformer B into mod KVA of the transformer A into mod of ZA by VB square is equal to KVA rating of transformer B into mod of ZB by VB square. Then we can say that ZA per unit is equal to ZB per unit. So therefore, if you want to share the load proportional to their KVA ratings, then the per unit impedance on the individual must be always equal. So therefore, to share a load proportional to the KVA rating, the per unit impedance on the individual base must be always equal. Then only we can say this is going to get happen. So therefore, simply we can say that to share the load proportional to the KVA ratings, always the per unit impedance on the individual base must be equal. So basically here you have to do the cross multiplication of these two things and do the division by VB square. Then you are going to get the per unit impedance on the individual base must be equal. Then only they can share the load which is proportional to their KVA ratings. So this is the point that you always have to remember. So to share the load proportional to the KVA ratings, the per unit impedance on the individual base must be always equal. So if you want the actual vector values, I already told you SA by SB is equal to ZB by ZA whole conjugate. These are actual values. If you want magnitude values, means mod of SA by mod of SB is equal to mod of ZB by mod of ZA. So less per unit impedance transformer shares its full KVA rating to the transformer. I have already told this one because they are inversely proportional. So less is the leakage impedance, means more is the sharing of the transformer to the load. So less per unit impedance transformer shares its full KVA rating to the load. So less per unit impedance transformer shares its full load KVA rating to the load. So less per unit impedance transformer shares its full load KVA rating to the load. So less per unit transformer will share the full KVA rating to its load. So now we'll see the cases, case 1 and case 2. Suppose when ZA and ZB are in ohm, then what we have to do? If in the question they have given ZA and ZB are in ohm values, then what we have to do? See, just go for this one. SA is equal to, just now we have shown, SA is equal to SL into ZB by ZA plus ZB whole conjugate, and similarly SB is equal to SL into ZA by ZA plus ZB whole conjugate. Then what is net SL? SL is equal to SA plus SB. All these are vector quantities. So independent of transformer KVA ratings, So in the question, if they given the ohmic values ZA and ZB, irrespective of the KVA ratings of transformers, just go for this one. So therefore, if when ZA and ZB are given in ohmic values, irrespective of the KVA ratings of the transformers, just use this blindly, these two formulas, to know each and everything. What is the amount of KVA shared by transformer A and KVA shared by transformer B. All these things you can easily get for case 1. Case 1 is very easier. So whenever the ZA and ZB are in ohms, just use these concepts, then independent of transformer KVA ratings. Suppose when ZA and ZB are given in per unit, then what we have to do? When ZA and ZB are given per unit, then calculate both the impedance on same KVA and then apply the case 1 formulas. Assume any KVA you want. So basically, suppose when ZA and ZB are given per unit, then calculate both the impedance on same KVA and then apply these new impedances on the above formulas. So then apply on the case 1 formulas. Assume any KVA you want. So this is the thing that you always have to remember. So whenever the ZA and ZB are given in per units, then calculate both the impedances on same KVA. Then you have to calculate on the same KVA. So you should calculate the per unit values on the same KVA and then apply the case 1 formulas. Then then apply the case 1 formulas to get the value of SA and ASB. So if they are given the ohmic values means case 1, don't think about KVA readings, just apply the basic formulas. If they are given the per values means now calculate the ZA and ZB per values on a common KVA rating, and then apply the case 1 formulas to know each and everything. So assume any KVA you want, you will get the same result. Assume any KVA you want, you will get the same result. So whenever ZA and ZB are given per unit, then calculate both the impedance on same KVA and then apply the case 1 formulas. Assume any KVA you want. So small concept here. Suppose load is receiving W watts active power. Then what is the active power sent by transformer 1 and active power sent by transformer 2? Same thing, just go for this magnitude values. So the active power sent by transformer 1 is equal to W into Z2 by mod of Z1 plus mod of Z2. Magnitude values you have to consider. Similarly, P2 is equal to W into mod of Z1 by mod of Z1 plus mod of Z2. These units of PT1 and PT2 are the watts, and PT1 plus PT2 is nothing but total W. So therefore, if you do the addition of these two things, we are going to get the W. So therefore, see, this is a load is going to receive W watts. It is the active power. Then the active power sent by transformer 1 is equal to W into mod of Z2 by mod of Z1 plus mod of Z2. Similarly, if the active power sent by transformer 2 is equal to W into mod of Z1 by mod of Z1 plus mod of Z2. So the units of powers is nothing but watts. So total power, the total active power sent by transformer 1 and transformer 2 is equal to load active power received. So PT1 plus PT2 is equal to W. So now we are going to discuss another concept which is called as the all-day efficiency. So percentage of efficiency all day of a transformer is equal to ratio of the output energy in a day kilowatt hour by input energy in a day. So all day efficiency means for a transformer, the percentage of efficiency all day is equal to ratio of the output energy in a day kilowatt hour by input energy in a day kilowatt hour. So basically for a transformer, if you want to find what is the overall efficiency, all day efficiency in a day, so efficiency, the percentage of efficiency all day is equal to output energy in a day in a kilowatt hour by input energy in a day in a kilowatt hour. So all day efficiency means the percentage of efficiency all day is equal to ratio of the output energy in a day kilowatt hour by input energy in a day kilowatt hour. So now we will discuss the open delta connection. So open delta connection now we are going to discuss. So take one case, delta connection. Suppose you take a delta connection means we can say that the transformer, the three-phase transformer is connected in a delta fashion. It is basically a three-phase transformer. It is connected in a delta fashion. The primary is in the star connection and the secondary is also, the primary is in the delta connection and the secondary is also in the delta connection. So this is the terminals capital A, capital B and capital C. So these are the small terminals, small a, small b and small c. So we are going to supply to a load. Here. So now you will see what is going to happen. So let kVA of the delta is equal to kVA of the load 1. So this is the load 1. So I am going to assume that I am going to keep a full load kVA. The load kVA is equal to kVA of this delta, or we can say delta connection transformer, or this three-phase transformer of delta. So kVA rating of this delta transformer is equal to kVA of the load I am going to apply, load 1. Then suppose if you see full load applied, then what is the kVA of the transformer? kVA of the transformer 1 plus kVA of the transformer 2 plus kVA of the transformer 3. Suppose if we are going to do the connection with a 3 single phase transformers, then what is the overall kVA? It is summation of the individual transformer kVAs, which is kVA of the transformer 1 plus kVA of the transformer 2 plus kVA of the transformer 3. Suppose if you are going to connect the 3 single phase transformers into the delta connection, the overall rating of the delta connection is equal to kVA of the transformer 1 plus kVA of the transformer 2 plus kVA of the transformer 3. Whenever we are going to apply the full load, we are going to apply for this connection of this delta transformer. Then kVA of this delta is equal to, kVA of this delta is equal to root 3 VL IL conjugate. See here, root 3 VL IL conjugate. Here you can see clearly that line voltage is equal to phase voltage for delta. So Vp, and line current is equal to root 3 times the phase current. So take the conjugate, we are going to get root 3, it is going to come upward, outward we are going to get 3 Vp Ip conjugate. So we can say simply that. So kVA of this delta delta transformer is equal to 3 Vp Ip conjugate. So listen carefully, that is kVA delta delta is equal to root 3 VL IL conjugate. So VL is equal to Vp and IL is equal to root 3 Ip because of delta connection. So therefore take the conjugate, we are going to get 3 Vp Ip conjugate. So therefore this is called as Vp means phase voltage, Ip means phase current. So kVA delta delta is equal to 3 Vp Ip conjugate. So this is the equation 1 I am going to consider. So open delta connection means out of these three transformers, one transformer got some fault. So I am going to remove the transformer. It is going to have some primary winding and secondary winding. So I have removed the primary winding and the secondary winding of the transformer. So now it is called as the open delta connection means only two transformers are there but not the third transformer. Third transformer we have removed it because of certain fault is applied is there. So therefore now this is the new transformer we are going to get. It is called as the open delta connection. So this is the capital A, capital B and capital C. This is small a, small b and small c. So we are going to apply a load of load 2. See now let kVA of this VV is called as the open delta connection because it is in the shape of a V type. So kVA of this VV is equal to kVA of the load 2, full load applied. This is a new load. This new load is equal to rating of this open delta connection. So kVA of this open delta, kVA of VV is equal to kVA of the load 2, full load we are going to apply. Then what is the kVA rating of this open delta is equal to root 3 VL IL conjugate. So VL is equal to Vp and IL is equal to Ip because whatever the line current is equal to phase current. So therefore line voltage is equal to phase voltage and line current is equal to phase current. Because of this it is open. So therefore Vp Ip conjugate. So VL is equal to Vp and IL is equal to Ip. So you are going to get root 3 Vp Ip conjugate. So this is called as a second equation. So kVA rating of this open delta is equal to root 3 Vp Ip conjugate. So this is the second equation. Now I am going to divide the second equation by first equation I am going to get. So what is the second equation? kVA of the open delta connection is equal to root 3 Vp Ip conjugate, whereas kVA of the delta delta connection is equal to 3 Vp Ip conjugate. So common terms are going to get cancelled. So finally we are going to get 1 by root 3. So 1 by root 3 is nothing but 0.577. So simply we can say that here the kVA rating of this open delta connection is equal to 57.7 percentage. It is a 57.7 percentage of the kVA of the delta delta transformer. So kVA of the open delta is equal to 57.7 percentage of the kVA of the delta delta connection. So we can say that because of this one transformer is removed, the new rating is lesser than the old rating. So kVA of the open delta is equal to 57.7 percentage of the kVA rating of this delta delta transformer. So to transfer same kVA by open delta, the current required is, suppose if I want to transfer the same amount of kVA as the delta delta connection, what is the current I need required? So to transfer the same kVA by open delta, the current required is means I want to transfer the same amount of kVA means I want to transfer the delta delta kVA to the load, then what is the current I should require? Or when same load connected for both to draw same kVA. So if you connect the same load for both delta delta or open delta, then we can see how much amount of current is required to give that load kVA. So therefore kVA of the delta delta just now we have seen just 3 Vp Ip conjugate, and kVA of the open delta is equal to root 3 Vp Ip dash conjugate. Now we are going to go for the Ip dash conjugate because of different phase currents. So now I want to equate them. Then if you equate these two things, we are going to get finally Ip dash Vv is equal to root 3 Ip delta delta. So therefore simply we can say that the phase current of this open delta must be root 3 times the phase current of this delta delta connection. Then only we can transfer that amount of kVA to the load. So therefore if you want to transfer the same kVA by open delta, the current required is, or when same load connected for both to draw the same amount of kVA, the current required by the phase current required by the open delta is equal to root 3 times the phase current of the delta delta connection. So the phase current of this open delta should be root 3 times the phase current of the delta delta. Then only it can transfer the original amount of kVA, that is delta delta transformer, to the load, or we can say same load of rating. Suppose if I am going to connect a load of kVA rating of delta delta, this I am going to calculate for both delta delta and also for the open delta. Then this much amount of current is required by this open delta to satisfy that load kVA. So now we are going to analyze some more important concepts for this open delta. So this is the capital A, capital B, capital C, small a, small b and small c. So now I am going to connect a star load of equal impedance Z. We can say basically it is a equivalent, or you can say star connected balanced load, and Z is basically lagging load. It is basically lagging load with a neutral point N. So this is the connection we are going to give. So this is A connection, B connection and C connection. So line current is IA, line current is IB and line current is IC. So now I am going to keep a load. This load kVA itself is equal to this rated kVA of this open delta connection. So kVA of the open delta is equal to kVA of the load we are going to assume. So I am going to assume in this fashion, and then I am going to proceed to see what is going to happen. So because it is going to generate the power, so current is going to flow in this one means it is a positive and negative. So current is going from positive means it is generating the power. Similarly here it is positive and negative means it is generating the power. So these two transformers are going to generate the power to this load. So now basically now I am going to draw the phasor diagram. So now I am going to draw the phasor diagram. As you can see clearly, as it is the balanced star load, so VAN, then comes the VBN, and then comes the VCN. So all these things are nothing but they are phase difference by 120 degree. So this is VAN, this is VBN, and this is VCN. So you can see clearly IA is going to pass through VAN. So therefore through IA is passing through Z across the voltage of VAN. So therefore as it is a lagging load, so IA is going to lag the VAN by small amount of angle phi. So IA is going to lag the VAN by angle phi. Similarly IB is going to pass through VBN. So the impedance of Z. So IB is going to lag VBN by phi. So simply we can say that IB is going to lag the VBN by small amount of angle phi. Similarly IC is the current which is flowing through the impedance of Z across the voltage VCN. So therefore the IC is going to lag the VCN by angle phi. So therefore we can see simply IC is going to lag the VCN by at an angle of phi. Then I want to know what is the line voltage VBA. So now I want to find what is the line voltage VBA and VCA. So what is VBA? VBA is nothing but VBN minus VAN. So this is VBN minus VAN means this side. So therefore this is the minus VAN. So if you do the vector addition of these two vectors, so now if you see clearly this minus VAN and VBN, their phase angle, their angle between them is 60 degree. Both are equal vectors. So therefore again 30 degrees we are going to get here. So this is 30. So this is nothing but VBA. So VBA is equal to root 3 times the magnitude of the VAN or the magnitude of the VBN. Similarly VCA, I want VCA. VCA is nothing but VCN minus VAN. So this is VCN and this is minus VAN. Again phase angle between the VCN and minus VAN is 60 degree. So therefore if I take this VCA, it is going to have a phase difference of 30 degree because of both having the same equal magnitudes. So this is VCA, it is going to have angle of 30 degrees with respect to VCN. So now what is the complex power sent by the transformer 1? So what is the complex power sent by the transformer 1? So S1 is equal to what is the voltage VBA bar and complex current conjugate. Current conjugate is nothing but IB magnitude of the here VBA and the IB conjugate. So I've already told you what is the complex power sent by the transformer 1 is equal to, which is VBA. So this is VBA bar into magnitude of IB into phase angle between the VBA and IB whole conjugate. Rating of the transformer 1 in terms of kVA. Similarly, the kVA rating of the transformer 2 is nothing but S2 is equal to, which is VCA bar. So VCA bar into magnitude of IC into phase angle of VCA and IC whole conjugate. Because complex power is equal to V into I conjugate. So like that we are going to write in terms of the vector quantities. This is called as the kVA rating of the transformer 2 in terms of kVA. Then what is VBA? VBA is equal to VBN minus VAN and VCA is equal to VCN minus VAN. So this we are going to get VBA and this we are going to get VCA. So what is the phase angle between the VBA and IB? So VBA and IB is nothing but 30 minus 5. Similarly, the phase angle between the VCA and IC is equal to 30 plus 5. So you can see clearly the phase angle between the VBA and IB is nothing but 30 minus 5, and the phase angle between the VCA and IC is equal to 30 plus 5. So now you can substitute these phase angles in this above relation. So we are going to get S1 is equal to VBA is nothing but phase voltage. So VP into IP into, then what is the angle between VB and IB, which is 30 minus 5 whole conjugate, is nothing but simply we are going to get VP IP into 5 minus 30, because conjugate means keep a negative, we are going to get 5 minus 30, equation 1. And the KV rating of the transformer 2 is equal to VCA is nothing but phase voltage, which is VP, into IC is nothing but phase current, so IP into, at an angle of VC and IC phase angle is 30 plus 5. So if you see clearly, one important point I missed here. So if you take VB as a reference, then the IB is going to, and then the IB is going to lead. So if you take VB as reference, then IB is going to get lead. So therefore, simply we have to give a positive. So VP into IP into plus of 30 minus 5 at the angle of conjugate, because I am going to assume this as a reference phasor. So this voltage as reference phasor. So VP into IP into, this is current is going to lead here. So plus 30 minus 5 whole conjugate. So you are going to get this one. Whereas here, if I take VC as a reference, then the current IC is going to lag here. So therefore, current represented will be negative. So IP into minus of 30 plus 5. So this is the representation. So take for the conjugate, then we are going to get VP IP into 5 plus 30. So equation 1 and equation 2. So listen carefully. Here I have taken VB as a reference. Then the current is going to lead here. That way it is positive sign. Whereas if you take VC as a reference, the current is going to lag, IC is going to lag. That is the reason I am going to take here negative sign. So this is the equation 1 and equation 2. So VP IP into at an angle of 5 minus 30 for transformer 1, VP IP at an angle of 5 plus 30 for transformer 2. So this is the equation 1 and equation 2, where phi is called as the load, you can say the load power factor angle. Then, but if kV of the VB is equal to kV of the load is equal to, already I have told you, kV of the open delta is equal to kV of the load is equal to root 3 VP IP. So root 3 VP IP. So root 3 VP IP. Then VP IP means just do the division by root 3. So S1 is equal to kV of open delta by root 3 into at an angle of 5 minus 30 degree. S2 is equal to kV of the open delta by root 3 into 5 plus 30. So this is for whenever the load kVA is equal to kV of the open delta transformer. Then what is the power factor of the transformer 1? Power factor of the transformer 1 is nothing but this is the phase angle. So this is the phase angle between their corresponding voltage and corresponding current. So this is the phase angle between the corresponding voltage and the corresponding current of a transformer 1. And this is the phase angle between the corresponding voltage and the corresponding current of this transformer 2. So this 5 minus 30 is the angle between the VBA and the IB. Similarly, this 5 plus 30 is the angle between the VCA and the IC. All these things I have already told you. So this is the phase angle between them. So now, see, you can go for 30 minus 5 or 30 plus 5. You can go anything because cos is always positive. If you go for negative sign and positive sign, it is always going to give you same result. Then what is the power factor of the transformer 1, which is cos of 5 minus 30, and the power factor of the transformer 2 is nothing but cos of 5 plus 30. So this is a point that you always have to remember. See, I have already told you 30 minus 5 is the phase angle between the VBA and the IB for the transformer 1, whereas 30 plus 5 is the phase angle between the for the transformer 2 VCA and the IC. So you can go for this 5 minus 30 or 5 plus 30. Anything we are going to get the same result because cos is always function of positive, always positive. If you take negative or positive, you are going to get the same result. So therefore, the power factor of the transformer 1 is equal to cos of 5 minus 30, and the power factor of the transformer 2 is equal to cos of 5 plus 30. So this is the power factor of the transformer 1 is equal to cos of 5 minus 30, and the power factor of the transformer 2 is equal to cos of 5 plus 30. One is 5 minus 30 and one is the 5 plus 30. So power factor means we can say it is the phase angle between the corresponding voltage and the corresponding current. That is the phase angle. So power factor means take the cos of that function, cos of that angle. That is the meaning of this one. So for a transformer 1, I have already told you 30 minus 5 is the phase angle between the VBA and the IB. Whereas the transformer 2, the power factor angle is the phase angle between the IC and the VCA. So their angles we know. Just if you go for this one or if you go for this one, everything is always same. So power factor of transformer 1 is equal to cos of 5 minus 30, and the power factor of the transformer 2 is equal to cos of 5 plus 30. That is what I am trying to tell. So this is the condition only when the kV of the load is equal to kV of the load is equal to kV of this open delta. So this both the units are in terms of the kVA. Suppose if whenever the kV of the load is not equal to kV of the open delta, then we have to use this formula, which is S1 is equal to kV of the load by root 3 into 5 minus 30 degree, and S2 is equal to kV of the load by root 3 into 5 plus 30 degree. So this is the formula that you always have to use. So therefore the kV of the load is not equal to kV of the open delta. So this is the thing that you always have to remember. So therefore whenever if the kV of the load is equal to kV of the transformer, then you have to use this formula. If the kV of the load is not equal to kV of the transformer, use the kV of the load. So always prefer to use the kV of the load. So always try to use the kV of the load. It's a special case here. So therefore the S1 is equal to complex power surrounded by the transformer 1 is equal to kV of the load by root 3 into 5 minus 30 degree, and the power factor of the transformer 1 is equal to cos of 5 minus 30. Whereas the complex power surrounded by transformer 2 is equal to kV of the load by root 3 into 5 plus 30, whereas the power factor of this second transformer is equal to cos of 5 plus 30. That is the thing that I am trying to say from the all this time. Suppose when Z is equal to R UPF load, then what is going to see? What we are going to get? Suppose if we are going to connect a pure resistive load, then what is going to happen now? We are going to see whenever Z is equal to R UPF load, so therefore the power factor angle of the load is equal to 0 because it is a UPF load. Then what is the value of S1? S1 is equal to just now I have seen it is VP IP into at an angle of 5 minus 30 degree, and S2 is equal to VP IP at an angle of 5 plus 30. So here pi is equal to 0. So substitute here VP IP at an angle of minus 30, VP IP at an angle of plus 30. So if you do the expansion, we are going to get finally root 3 by 2 into VP IP minus J VP IP by 2. If you do the expansion of this one, we are going to get root 3 by 2 into VP IP plus J of VP IP by 2. So the complex power sent by the transformer 1 is root 3 by 2 into VP IP minus J into VP IP by 2, whereas the complex power sent by the transformer 2 is equal to root 3 by 2 into VP IP plus J of VP IP by 2. So we can see clearly the active power sent by the transformer 1 is root 3 by 2 into VP IP, which is equal to half of the kV of the open delta connection, which is half of the kV of the open delta. Whereas similarly the active power sent by the transformer P2 is equal to T2 is equal to root 3 by 2 into VP IP, which is also half of the kV of the open delta transformer. So you can see clearly both the values are always equal. So the active power sent by the transformer 1 is equal to active power sent by the transformer 2. So P1 is equal to P2. Then what is the reactive power sent by the transformer 1, which is minus VP IP by 2. Then what is the reactive power sent by the transformer T2, which is plus VP IP by 2. So we can say that one transformer is sending the reactive power and other transformer is accepting that reactive power. So if transformer T2 is sending the reactive power, it is absorbed by the transformer T1. So this is the meaning of this one, because load is not absorbing any reactive power. So whatever the reactive power sent by the transformer T2 is being absorbed by the transformer T1. That is the meaning of this one. Active power sent by the transformer 1 is equal to half of the kV of the open delta transformer, and the active power sent by the transformer T2 is equal to half of the kV rating of the open delta, and both the values are always equal. And second transformer is sending the reactive power. That same reactive power is absorbed by the transformer 1. P1 is equal to P2 is equal to half of kV of the open delta whenever the kV of the load is equal to kV of the open delta, whereas it is half of the kV of the load whenever the kV of the load is not equal to kV of the open delta. So this is the meaning of this one. So the active power sent by the transformer 1 and the transformer 2 both are equal for a purely resistive load. It is equal to half of the kV of the load. Half of the kV of the load. So whenever the load kV is equal to open delta, means use this formula, otherwise use this formula. So generally it is a special case, so you have to use this general formula. So S2 is going to deliver the reactive power to S1, and only reactive power goes from both the transformers to load. So we can say that S2 is going to deliver the reactive power to S1, and only active power goes from both transformers to load. So both the transformers are going to send the active power with equal values to the load, and the second transformer is going to send that reactive power to the transformer T1, because load is not going to accept any reactive power because it is a purely resistive load. So now we are going to discuss another new concept which is called as the Scott connection. Scott connection means it is going to transform three-phase system to two-phase system. So whenever if you want to transform from three-phase supply to two-phase supply with the help of transformers, then we are going to prefer this Scott connection. So if you want to transfer a three-phase supply to two-phase supply with the help of transformer, then we are going to use this Scott connection to make that happen. So with the help of Scott connection, we are going to transform the three-phase supply system to two-phase supply system. So what is the three-phase balance system, or you can say three-phase balance supply system? Means the voltage vectors of equal magnitude, and they are going to have a phase difference of 120 degrees between them. So this is VA, VB and VC, all are of equal length or equal magnitudes with a phase difference of 120 between them. If you want to convert this into two-phase system, two-phase balance system means there will be two voltages of equal length and their phase difference is 90 degree. This is called as the two-phase balance voltage system or balance supply. So we can say we can convert from three-phase to two-phase or two-phase to three-phase. Anything is possible with the help of this Scott connection for this transformer. So three-phase balance supply means the voltages of equal magnitude and they are going to have a phase difference of 120 degrees between them. And the two-phase balance supply system means the voltages of equal length and the phase difference is 90 degree. Now, to make this happen, the type of connection we are going to choose is this one. To make this happen, we are going to choose. So to make this happen, we are going to choose two transformers. One is primary transformer and the other is the TZ transformer. So these are the two transformers we are going to choose, which are the primary transformer and the secondary transformer. So for the primary transformer, this is the primary winding. So the primary winding we are going to make into two halves. The total turns in the primary winding is N1, but we are going to make it into two parts, which is N1 by 2 and N1 by 2. So this is the secondary of the primary transformer. So the number of turns is N2. Similarly, the TZ transformer, this is the primary winding. So it is a variable one. So we are going to vary the turns of this primary winding, and this is the secondary of this TZ transformer. So this is the N2 turns. So you can see clearly the turns of secondary on both the transformers is same. The number of turns is same. So therefore, if this is the dot for this one, this is the dot for this one, and this is the dot for this one, and this is the dot for this one. So now here we are going to have three terminals: terminal A, terminal B, and terminal C. So because this is the primary winding of TZ transformer and this is the primary winding of this primary transformer. So therefore, we are going to give three-phase balance supply for terminal A, terminal B, and terminal C. And this is the secondary of this TZ transformer, and this is the secondary of this primary transformer. Let me assume the voltage across the TZ transformer is plus or minus VA, and the voltage across this primary transformer is plus or minus VB. It positive at the dotted terminal, positive at the dotted terminal. See, let me assume here M is the midpoint, and from this point we are going to vary the turns on this primary of this TZ transformer, and this point is I am going to assume it as M. So always voltage VA is always in phase with the VAM. So whatever the voltage across VAM and the voltage VA, this both are in always phase with respect to each other. Similarly, VB is always in phase with respect to VBC. So VBC and VB both are always in phase. Similarly, VA is always in phase with respect to VM, and VB is always in phase with respect to VBC. So now, as I have already told you that the balance supply, we are going to give a balance supply. So therefore, magnitude of VAB is equal to magnitude of VBC is equal to magnitude of VCA is equal to VL, because the line voltages are always same. The supply line voltage is always same. So magnitude of VAB is equal to magnitude of VBC is equal to magnitude of VCA is equal to VL. VL we are going to get. So now, as I have already told you, in a three-phase balance supply, I have already told you VA, VB and VC. So VA, VB and VC. With the help of that, we are going to make a triangle. So we can get a triangle. If you do the rearrangement, we are going to get a triangle. So line voltages. So here you can see clearly this is called as VAB, VBC and VCA. So therefore these are the voltages we are going to get in this in a triangle fashion. I have already told you these line voltages have a length of VL for each and every one because they are balance supply. So this is the length is VL, this is VL and this is also VL. But you can see clearly M is the midpoint across the B and C terminal. So M is the midpoint across the B and C terminal. So therefore if this is a midpoint across this B and C, so it is off of this one which is VL by 2 and VL by 2. Now I am good. So this is called as a VAM. So VAM is nothing but this is the voltage VAM. So this is called as a VAM. So this is called as a VAM. If you draw a straight line, it is perpendicular to this base. So it is perpendicular to the base. I have already told you VAM and VA are always in phase. VAM and VA are always in phase. Similarly, VBC and VB are always in phase. I have already told you VBC and VB are always in phase. So this is having a length and this length are always same and you can see both are perpendicular to each other. Yes, this is possible. So this we got. So this is called as the balanced two-phase supply. Then what is VAM? So VAM is equal to by applying the Pythagoras theorem, which is under root over VAB whole square minus VMB whole square. VAB is equal to VL and VMB is equal to VL by 2. So if you substitute here, we are going to get root 3 by 2 into VL. So VAM is equal to root 3 by 2 into VL. So I have already told you. So secondary voltage. So VA by VAM is equal to N2 by N. N is the number of turns of the primary winding of this teaser transformer. So VA by VAM is equal to N2 by N. So what is the value of VA? VA is equal to N2 by N into VAM. Similarly, VB by VBC is equal to N2 by N1 because total turns on the primary of the primary transformer is N1. So therefore, VB by VBC is equal to, so VB by VBC is equal to N2 by N1. So therefore, VB is equal to N2 by N1 into VBC. I have already told you these two voltages should have equal magnitudes. So equate these two values. Then if you equate these two values, we are going to get N2 by N, VAM is equal to N2 by N1 VBC. We know VAM is equal to VL and we also know what is the value of VBC. VBC is equal to VAM is equal to root 3 by 2 VL and VBC is equal to VL. So if you equate these two equations, finally we are going to get capital N is equal to root 3 by 2 into N1. So therefore N is equal to root 3 by 2 is nothing but 0.866 or you can say 0.867 N1. So therefore if the number of turns on the primary of the TZ transformer is 0.867 times the N1. N1 is the total number of primary, N1 is the total number of turns of the primary transformer. If this is the ratio, if this is the case, then only we are going to get a balanced two-phase supply we are going to get. Then only we are going to get a balanced two-phase supply. So N is equal to N is equal to root 3 by 2 into N1 or simply N is equal to 0.866 N1. At this condition only we are going to get a two-phase balance supply at the output of the secondaries of the primary transformer and the second TZ transformer we are going to get. So three-phase supply is given to ABC terminals. I have already told you three-phase supply is given to the ABC terminals. Then we are going to get a two-phase supply across the secondaries of the primary transformer and the TZ transformer. I am going to connect a balance load. So now what is going to happen? Suppose if I connect a balance load, you will see each and everything. So now I am going to connect a balance load here for the secondaries of the TZ transformer and the secondary of the primary transformer. So this is basically a primary transformer and this is a TZ transformer. Connecting the balance load. So this is the balance load means equal loads of equal value. Loads of equal value means balance load. So this is Z and this is Z. I have already told you this is the primary transformer. So primary transformer is the total number of turns in the primary winding is N1. So we are going to cut into two parts, N1 by 2 and N1 by 2. Similarly, this secondary, we are going to, the secondary winding of primary transformer is going to have a number of turns of N2. This is the dotted terminal and this is the dotted terminal. So we are going to connect to a load. So as the load is kept here, the voltage is equal to VB and the load current is IB. Similarly here, for this secondary of the TZ transformer, I am going to connect a load Z. So what is the voltage here? Plus or minus VA and the load current is IA. Already I have already told you, I am going to give a three-phase supply for these terminals A, B and C. So this incoming current is IA, incoming current is IB, and incoming current is IC. So whatever the current here, it is going to flow through this one because it's open circuit. So whatever the current here, it has to flow in this direction. So this is the point, midpoint M. So this current is going to divide into two parts, IA by 2 and IA by 2. So what is the net overall current here, which is IB minus IA by 2? What is the net overall current in this winding, which is equal to IC minus IA by 2? So this is the thing that you always have to remember. So I've already told you for a balanced connected, so mod VA is equal to mod VB, because I've already told you N is equal to root 3 by 2 times of N1. So whenever N is equal to root 3 by 2 times of N1, at this point we are going to keep, whenever the primary terms is equal to root 3 by 2 N1, we are going to get a balanced voltage. So VA is equal to VB. So VA is equal to VB, and also load is also balanced. So therefore mod of IA is equal to mod of IB. So as the N is equal to root 3 by 2 N1, we are going to get a balanced voltage, and load is also balanced. So therefore mod of IA is equal to mod of IB. Now I am going to equate the MMF of this is a transformer, primary and secondary. So N into IA is equal to NT into IA. So N into IA is equal to N2 into IA. Now we know the value of N. N is equal to root 3 by 2 N1. So if we substitute here, finally we are going to get IA is equal to 2 by root 3 into N2 by N1 into IA. Similarly, I want to equate the MMF for this primary transformer also. Then what we are going to get, which is the primary winding of this primary transformer, which has the total number of turns is N1, and the overall current is from B to C, which is IBC. So N1 into IBC is equal to N2 into IB. So you can see IBC is the net amount of current which is flowing from B to C. So therefore N1 into IBC is equal to N2 into IB. So what is the value of IBC? IBC is equal to N2 by N1 into IB. So now IA is always parallel to small ia, and IBC is always parallel to IB. So this is a point that you always have to remember. IA is parallel to a small ia, and the IBC is parallel to the IB. So you can see that the primary current in the teaser transformer should be parallel to the secondary current in the teaser transformer. Similarly, the primary current in the primary transformer should be parallel to the secondary current in the primary transformer. So IA is parallel to IA, IBC is parallel to IB. So with the help of two above equations, so you know these two equations, IA and IBC. Just do the division of these two equations. What you are going to get finally, N2 by N1 are common, it is going to cancel. And also I have already told you IA is equal to IB because voltage is equal and impedance is also equal. So IA is equal to IB. So these are also going to get cancelled. So therefore IA by IBC is equal to 2 by root 3. So IA by IBC is equal to 2 by root 3 we are going to get. And I have already told you, as it is a balanced supply. So balanced supply means the line currents are also equal. So magnitude of IA is equal to magnitude of IBC is equal to magnitude of IC we are going to get, because it's a three-phase balanced supply. So magnitude of IA is equal to magnitude of IB is equal to magnitude of IC. Now I am going to draw this vector diagram. You see clearly. So this is a triangle. So you can see this is basically a triangle. So you can see basically this is a triangle. So now listen carefully. For this triangle, what is going to happen is, so this I am going to take a reference. So I have already IA. So IA, this is IA, this is IB, and this is IC. These are the three-phase balanced supply of equal length, and they have a phase difference of 120 degree. So IA and IB have a phase difference of 120, IB and IC has a phase difference of 120, and IC and IA has a phase difference of 120, because these are the balanced supply. And now I've already told you capital IA is parallel to small ia, and also this IA is parallel to IA. So this is parallel means this is also parallel. So now I've already told you this is the voltage VA and this is the voltage VB. Both are of equal voltage, of equal lengths, and they are perpendicular to each other. And the currents are also equal. So this is IA. It is going to lag with respect to small amount of phi, because it's a lagging load. So balanced load we are going to get, it is a basically lagging load. So current is going to lag, and it is parallel to this one, and it is parallel to IA. What is the value of net current IB? IB is equal to IBC minus IA by 2. So what is the net current in the winding from the terminal IB is nothing but IB is equal to IBC minus IA by 2. So therefore IB is equal to IBC minus IA by 2. So now you know the value of IA. So IB is equal to IBC minus IA by 2. So now I want to draw what is the IBC. So IBC is nothing but IBN minus ICN. So this is IB, this is IC. So if you draw this vector diagram, we are going to get this is the IBC with an angle of, so this is angle, it is having an angle of theta. So this is having an angle of theta. So you can see clearly that it is going to have a small amount of angle theta. So therefore this is the angle theta with respect to IB. So IBC is equal to IB n minus IC. So IBC is equal to IB minus IC. So we are going to get this is the vector IBC. So therefore now IB is the vector addition of IBC minus IA by 2. So this is IA. Do the opposite of this one, minus IA by 2. So do the vector addition of these two vectors. We are going to get this one. So IB is equal to IBC minus IA by 2. Then what is IC? IC is equal to minus of IBC plus IA by 2. So IC is equal to minus of, so IC is equal to minus of IBC plus IA by 2. If this is plus IBC, then this is minus IA minus IBC and this is minus IA by 2. Do the vector addition of these two things, we are going to get this IC. So this is, if you do the vector addition of these two things, we are going to get this IC. And this is angle theta, because if this is theta, definitely this is also theta. So if this is theta, this is also again theta. Then what is the tan theta? So tan theta is equal to IA by 2 by IBC. So tan theta is equal to opposite by adjacent, which is IA by 2 by IBC. So tan theta is equal to IA by 2 by IBC. Then already we know the value of IA by IBC. So what is the value of IA by IBC? 2 by root 3 into 1 by 2. So we are going to get 1 by root 3. So tan theta is equal to 1 by root 3 means theta is equal to 30 degree. So therefore theta is equal to 30 degree we are going to get here. So theta is equal to 30 degree. So this is the theta, which is 30 degree. So now if you see clearly, so this is the IBC we are going to get. So this is the IBC. So this is the IBC. If this is 30, then definitely this is 90 degree, because the total angle is 120. If this is 30 means this has to be 90 degree. So therefore this is IBC means this is also IB. So IB is parallel to IBC and IA is parallel to IA. So angle between them is 90 degree. So here also angle between them is 90 degree. So therefore IB is going to lag VB by small amount of angle phi. Phi is the power factor of the load. So you can see clearly IA and IB are also equal lengths and they are perpendicular to each other. So if you apply a three-phase balance supply and the loads are balanced load, then definitely the load voltages are also balanced supply, two-phase balance supply, and the load currents are also balanced supply. The phase angle between them is 90 degree. So this is the concept that we have to see here. IP is equal to IBC minus IA by 2. IC is equal to minus of IBC plus IA by 2. So this is the thing that I am trying to say here. I am trying to say finally is, if you connect a three-phase balance supply and the load is balanced load, then we are going to get a two-phase balanced voltage and also two-phase balanced currents we are going to get. These two-phase balanced voltages are perpendicular to each other and these two-phase balanced currents are also perpendicular to each other. That is the meaning of these things up to now we have studied. Suppose if you are going to connect an unbalanced load, then what is going to happen? If you are going to connect an unbalanced load, means of different loads, the loads of different values, then what is going to happen? Now we are going to study. So this is called as the three-phase. So this is the TZ transformer, this is the primary transformer. So this is the terminal A, terminal B, terminal C. So this is the primary of the primary transformer, secondary of the primary transformer. This is the primary of the TZ transformer and the secondary of the TZ transformer. So here, this is the terminal B, terminal C, this is the midpoint. Primary of it is divided into two parts, N1 by 2 and N1 by 2. And here, the overall current is IB. So this is the IBC is the overall current passing through B to C. So this is the secondary. We are going to connect a load of Z2 impedance. And this is the load voltage of VB. The load voltage of VB here. And the load of Z1 we are going to connect here. And the load voltage of plus or minus VA. And the load current is IA here. So I am going to give a at this terminal at M. So therefore the primary having a number of turns is equal to root 3 by 2 N1. So root 3 by 2 N1. N1 is the total number of turns of this primary transformer. Then we can see clearly, then if this is a condition, if you are going to give a three-phase balance supply, the load voltages, or you can say two-phase balance voltages we are going to get. So mod of VA is equal to mod of VB. But the loads are of different values, so the currents are also different values. So mod of IA is not equal to mod of IB. And I have already told you, IA is always parallel equal to IA and IB is always parallel to IBC. So if this is a current IA, it is going to pass through this here and it is going to divide into two parts because of equal impedance IA by 2 and IA by 2. Then what is the value of IB? IB is equal to, we can say IBC minus of IA by 2 and IC is equal to minus of IBC plus IA by 2. See, now we are going to draw the phasor diagram. So listen carefully here. This is the current IA, this is the current IB, and this is the current IC. See, as the line currents we can see clearly. So this is the line currents you can see clearly. So this is the line currents IA, IB, and IC. Then the theta1 is the phase angle between the IA and IC. Theta2 is the angle between the IA and IB, and theta3 is the angle between the IB and IC. Then because of this we are going to get a balanced voltages but not the balanced currents. So this is current IA and this is the current IB. So what I am trying to say simply here, simply you can see clearly that IBC, so IBC is equal to, what is the value of IBC? IBC is equal to N2 by N1 into IB. So simply we can say N1 into IBC is equal to N2 into IB. So IBC is equal to N2 by N1 into IB. Then what is the value of IB? IB is equal to IBC minus IA by 2, and IC is equal to minus of IBC plus IA by 2. So if you take negative, you are going to get in this fashion. So now IBC, so what is the value of IB? IB is the vector addition of IBC and minus IA by 2. So this is minus IA by 2 and this is IBC, because IBC is equal to IB minus IC. So you are going to get IBC in this fashion. So therefore, if you do the vector addition of the IBC and minus IA by 2, we are going to get IB in this manner. So now if this is IBC, then IB is parallel to IBC. So this is we are going to get IB. So IB is parallel to IBC and IA is parallel to IA. So the angle between IA and IBC is alpha. So here also same thing, alpha you are going to get. The IA is going to lag VA by angle phi 1 and IB is going to lag VB by angle phi 2, and alpha is the angle between the IA and IB. Both are of different lengths and also they are not perpendicular to each other. So if you connect a balanced load, if you are going to connect an unbalanced load, the line currents are also unbalanced of different magnitudes, and they are also, we can say they are not have phase difference of 120. So we can say whenever you connect an unbalanced load, the line currents are also unbalanced of different magnitudes and phase difference is not equal to 180, and also the load currents are also not unbalanced. They are unbalanced. So what I am trying to say finally, if you keep a balanced load, then the line currents in the primary, the line currents in the teaser transformer and the secondary in the teaser transformer, primary transformer, the primary currents are always balanced nature. If you are going to connect an unbalanced load, the primary line currents are unbalanced in nature. So listen carefully. Again, I am trying to tell you. See, whenever you connect a balanced load, the primary line currents are in balanced nature, and also the secondary currents are also balanced nature. Suppose if you are going to connect an unbalanced load, the primary line currents are unbalanced in nature and the secondary line currents are also unbalanced in nature. That is the meaning of this concept. So whenever we connect a balanced load, the primary line currents are balanced in nature. If you connect an unbalanced load, then the primary line currents are unbalanced in nature. That is the thing that I am trying to tell you from all this time.